Okay, so we're talking about the transmission of the continuous signal as a discrete signal, and we were learning about the different techniques by which this digitization can take place. So the delta modulation technique also has a role to play in the conversion of this continuous data stream into a discrete stream. So delta modulation is a technique which can be applied for the transmission of voice information, so audio information where 100% accurate representation is not particularly important. It's not fair to say that quality isn't important, but the signal can cope with some loss in the original information that's being communicated in the conversion into the discrete signal, allowing the original message to still be communicated, so it can cope with some amount of loss. With the delta modulation approach, it's the difference between the successive samples which are encoded into the stream of data which is being sent. So it's the difference between successive samples as opposed to the actual values of the samples themselves. Okay. So its main features are that the analog signal is approximated with a series of segments, and each segment of this approximated signal is compared to the original analog wave in order to determine whether to increase or decrease the relative amplitude. So the actual value which is sent is a measurement in relation to the previous value, whether it be an increase or a decrease in relation to the previous value. So the decision process for establishing the state of the bits which are sent is determined by this comparison. It is only the change of information that is sent. So it's the change of information in relation to the previous bit of information that is sent. So only an increase or a decrease of the signal amplitude from the previous sample is sent, and no change condition causes the modulated signal to remain at the same state of the previous sample. So if it was a 0, it can remain at a 0, or if it was a 1, it can remain as a 1. So it's only that change that is actually communicated when the delta modulation technique is applied. Okay, so quantization distortion or quantization error. So we mentioned this already briefly, but just to put it into a couple of slides, what is actually meant by this error or this distortion. So the distortion is the round off error. So whenever we are approximating the value of the continuous wave into our discrete finite set of symbols that are being communicated, this distortion results from a round off error, which results in a loss of the accuracy, a loss of the representation of the original continuous signal being sampled. Okay, so this signal is representing the value at any given moment within a finite set of possible values. So we want to restrict the range or the range of values which are actually captured in the continuous signal. We want to restrict those in order to communicate them within a finite set of possible values, which are the digitized values that are communicated. So if the signal value is, for example, 5.25 and the nearest possible values are 5 and 6, the signal can be rounded off to 5. And the difference between the represented value of 5, so this is our represented level of our continuous signal value, and the quantization error in this case is 0.25. Okay, so we have some loss in the accuracy of the digitized information in relation to the original set of data which was collected. So in this figure we have two plots. The red signal is the sample quantized one. The grey signal is unsampled. Okay, so the grey signal is the original signal. The dotted horizontal lines are the possible quantized signal values. The red signal should have the same values as the dotted line at any time. Okay, so the red signal should have the same values as the dotted lines at any time. These are our quantized levels that we want to create our discrete signal from. But the red corners do not exactly touch the grey signal. This is the quantization error. Okay, so the red corners do not exactly touch the grey signal, and this is the error. So we're either rounding up or we're rounding down. So a common use of this approach is in the conversion of a discrete signal, so a sampled continuous signal into a digital signal. Okay, so we want to make that conversion from our continuous signal into our discrete signal. Both of these steps, sampling and quantizing, are performed in analog to digital converters, with the number of levels being representing the continuous signal specified in bits. So a specific example is the compact disc, which is sampled at 44,100 Hz and quantized using 16 bits. Okay, so using those 16 bits, the actual value which is being represented can be one of 65,500 possible values. Okay, so every signal level can be represented according to a number of bits, which will be a power of 2. And in your tutorial on Wednesday evening, you'll actually get to experience the effect of this quantizing and the number of bits in terms of the effect that it has on the overall amount of data which is being communicated as a result. Okay, but this is just one example to contextualize where this is actually used in reality. So whenever used for voice transport, a 64 kilobits per second channel contains speech. Okay, so we have our analog speech signal. Sample this signal according to the rate of 8,000 samples per second. Each sample is encoded into an 8-bit code. Okay, so then we work out to our 64 kilobits per second channel. So if you want to actually go about calculating these quantization levels, how many levels should be used? What is an adequate number of levels in order to allow the original signal to be reconstructed? Okay, so one of the basic choices in this process is to determine the number of discrete levels to use. Okay, so we've got, this is our original signal here, whenever we're using 32 levels, whenever we're using 16 levels, and whenever we're using 8 levels. So you can see that there's a reduction in the representation of the digitized signal in relation to the original signal as the number of levels decline. Okay, wherever there's a greater number of levels actually used, the digitized signal more closely matches that original signal. Okay, but there's the higher overhead of applying such an approach. Okay, so the trade-off in this situation is the resulting quality of the signal, okay, versus the amount of data used to represent each sample. So if you have more signal levels, you'll have a higher quality signal, but there'll be more data which is actually needed to represent each sample. So there's a cost benefit here in the decision-making process. As a rule of thumb, however, you can say that with L levels, so with whatever number of levels, we need log 2 L bits to represent the different levels. So for example, if we're using our 8 levels to convert our signal, we'll need 3 bits in order to represent these different levels. Okay, so this is a calculation which you should be aware of, and you'll get some practice of actually applying that calculation in your tutorial on Wednesday night. But this is an important thing that you should be familiar with. Okay, so just to conclude this series of slides, the actual steps which are carried out. So whenever the quantization is the next step in the conversion of the signal so that it may be transmitted. So this is applied after we sample our continuous signal. So the result of sampling is a series of pulses with amplitude values between the maximum and minimum amplitudes of the signal. So we've got a series of pulses. They have different amplitudes between the maximum and minimum amplitudes of the signal. The set of amplitudes can be finite with non-integral values between the two limits. Okay, so we'll have a number of values within these two limits. So the following are the steps which are carried out in this process. If we assume that the original analog signal has amplitudes between maximum and minimum, we divide the range into a number of zones, each of height delta. Okay, so we assign values of 0 to L minus 1 to the midpoint of each zone, and we approximate the value of the sample amplitude to the quantized values. So if we assume that we have a signal and the sample amplitudes are between minus 20 and plus 20 volts, and we decide to have 8 signal levels, so we have a step size of 5 volts between each level of our reconstructed signal. So the quantization process selects the value from the middle of each zone. Okay, so we're applying the middle of each zone to that digitized value. So at the very start of these slides, we talked about the example of applying a range of values from minus 0.9, minus 1, up to 0.9 and 1. So we use a step size of 0.1 in this example, but this was just for presentation of the principle of how we actually assign values to a continuous signal. Computers do not represent numbers using decimal digits, so we use the binary digit instead, and this is just something that you should be aware of. Okay, so with B bits, we can represent 2 to the B distinct numbers. So if we've got 3 bits in our signal, we can represent up to 8 distinct numbers. So these should always be a power of 2, the number of bits representing our distinct numbers that we wish to communicate in our digitized signal.